So the third section here is work, energy and power, and a lot of the topics here the students should be familiar with from IGCSE, but you probably want to just repeat some of the information. First, you want to define work done. Work done is defined as the force acting upon an object multiplied with the displacement in the direction of the force. So you want to give an example to elaborate this. For example, if there is an object and there is a force pulling on this object in this direction, but the object is moving in this direction. Okay, so this is this is probably denoted by S. Okay. So if the object is moving along this surface here, but the force is pulling it in that direction, there are two ways of defining the work done in such a scenario. Either you see the direction of the force being applied and multiply that with the displacement along that direction, or another way of defining this, an easier way of defining this in this case, is look at the direction of the displacement and see the component of the force being applied in that direction. So in this case, the component of force being applied in the direction of the displacement would be F cos theta over here. So the work done will be, if S is the displacement, then the work done will be Fs cos theta. Notice that force is a vector, displacement is a vector, but you don't have to go into the details of a dot product, but just mention that work done is a scalar quantity. Okay, but you can have negative work done, so you want to also mention that, because some students think that work done can only be positive. So you want to mention that work done can be negative if the force applied is in the opposite direction of the displacement. Okay, that covers work done. After that, you want to mention kinetic energy and gravitational potential energy and examples of how an object at a height, when it falls, the gravitational potential energy gets converted to kinetic energy. There's a good example on in the notes on page in section 2.3.6, using the principle of conservation of energy. So how the total amount of energy is conserved in certain scenarios, and how a student can use that in the examination as a more efficient method to solve problems which would have a much longer solution using a kinematic method. So there is an example here which very nicely elaborates this. They give the kinematic solution and how it's a little lengthy or a little complicated, and that the energy principle, just by using conservation of energy, how the gravitational potential energy is conserved and it gets converted into kinetic energy, that gives a very short and concise solution to the same problem. So you want to mention this kind of an example. 2.3.7 is just listing different forms of energy, a little theoretical. Probably the student wants to take a quick read on this. Not very exam relevant. Alright, 2.3.8, as I mentioned in the previous part, is a description of elastic and inelastic collisions. So just mention that momentum is conserved in all kinds of collisions, but kinetic energy is only conserved in elastic collisions. After that is the definition of power, simply the rate of change of work, or the rate at which work is done, or also the rate at which energy is supplied. So you want to mention those various forms. So power can be defined as the change in work, or the rate of change of work with time. Work done is also defined as force multiplied by the distance traveled, okay, over time. And the rate of change of displacement, or the rate of change of displacement in this case, will be velocity. So power can also be calculated using force multiplied by velocity. Okay, so you want to give this. 2.3.10, simple definition of efficiency is the useful output over input in percentage. So it could be the useful work done, the work output, over the work input multiplied by 100%. Or it could also be the useful power output divided by the power input multiplied by 100%. That's just a basic definition of efficiency. Then 2.3.1 is important because you want to discuss a few problems where, for example, example 2 on page 26 is one very good example where the student has to use the principle of conservation of momentum and the conservation of kinetic energy. So in order to solve the problem. So this is like a combination of using momentum and energy equations in one problem. Yeah. And then from here we move on to the last section, uniform circular motion. Okay, the last section of chapter 2 is uniform circular motion. So suppose we have a stone extended by a string which is fixed at this point, and this stone is moved in a circular path, right? Okay, so let's say we have to draw the free body diagram for this stone. So the forces acting on the stone are one, the tension in the string over there, and the weight acting downwards. Okay, those are the only two forces acting on the stone while it's moving in the circle. Now, since the stone is not moving up or down, the acceleration in the vertical direction is 0. Therefore, okay, firstly, let's say the stone is extended at an angle theta over here. So this angle here will also be theta, right? So in the vertical direction, the forces are in equilibrium. Therefore, the vertical component of the tension here, T cos theta, okay, and the weight should be equal. So therefore, we have T cos theta equal to the weight. So the forces in the upward and downward direction are in equilibrium. Now we have a component of the tension along the horizontal axis here, which is T sine theta. Okay, there is no force outwards to actually balance out this force, this component of tension. So this is an unbalanced force, and this is the force that is making the stone move in a circle. Okay, so you want to explicitly mention that this force is the centripetal force. So therefore, the centripetal force is T sine theta. Okay, right. Also, the force from Newton's second law we know is the mass of the object, the mass of the stone multiplied by its acceleration. In this case, it's called the centripetal acceleration. Okay, from page 27 to 28 in section 2.4.2, there is a very nice derivation of the centripetal acceleration, which you probably want to discuss with the students in order for them to understand how you get the formula. But also make it clear to them that they're not expected to know the derivation, and that they can simply know that the centripetal acceleration is given by v square over r. Okay, where v is the linear velocity or the tangential velocity of the stone as it moves along the circle. So when the stone reaches here, the linear velocity is in that direction, always tangential to the circle, whereas the acceleration or the force, like over here the force is pointed towards the center of the circle. Over here again, when the stone is in that direction, if we resolve the forces, we will see that the force will be acting towards the center of the circle, and hence the acceleration is also always towards the center of the circle. Alright? So the centripetal acceleration is always towards the center of the circle, and its value is calculated with the tangential velocity v square over r, where r is the radius of this circle. Okay? So therefore the centripetal force, okay, which is as we calculated equal to T sine theta, is given by mv square over r. This is basically the basic concept for uniform circular motion. You can discuss a few examples of such kind of horizontal situations where the velocity is uniform in the circle. The next portion in 2.4.4, you have some situations where your object is moving in a vertical circle. So in that situation, you want to mention, for example, if you look at page 29, when the object is being moved in a vertical circle, at the bottom of the circle, the weight acts downwards and the tension acts upwards. So your centripetal force will be the tension minus the weight acting downwards. But when it's at the top of the circle, the tension is acting downwards and so is the weight. So the centripetal force will be the tension plus the weight. So you want to make sure the student understands this, and if you want, I like to do this. I also like to discuss the situations where in a vertical circle the object is at the sides. How is it that at the sides, or what happens at the sides of a circle? You might want to research this, and how in a Ferris wheel you can maintain a constant velocity even though you're moving in a vertical circle. So some of these interesting things you can go into discussion with the student if the student is interested as well. Okay, and that's pretty much it. Example 2 on page 30, you can ask the student to do. It's an example where they ask, if a motorcycle is going in a vertical circular loop, what's the minimum velocity required? I think it's a good example to strengthen the uniform circular motion concepts. So yeah, and that pretty much ends the chapter.